I mean, I hope you'll just raise questions as the panel goes on, but if you want to post things on a Google Doc instead, you can do that as well.
Or is it easiest to just like email?
Well, I'll put a link up there and see that I can monitor it.
Okay. So while Chris is doing that, we're going to have our final session today will be a panel discussion on what I'm sure will be an entirely uncontroversial topic, namely, what is the ontology of QFT? Okay. So I think the way we'll proceed is that I'll give each of today's speakers a few minutes to kind of suggest which part of the territory you'd like us to focus our attention on, or at least, or perhaps if you're prepared, tell us what the ontology of QFT is. So I'll give you each a few minutes, and then we'll take questions from the audience. Okay? So, Noel, maybe we'll go in order of speakers.
So one thing I should say, sort of by way of kind of orienting this morning's talk, that kind of grew out of kind of three-part paper where I began by looking at other sorts of field ontologies for quantum field theory, with the idea of trying to articulate how those got around Baker's objections. And in the process realized that sort of the wave functional interpretations also potentially had ways of getting around some of Baker's objections. So, at least the way I sort of see it, three interesting, potentially viable kind of field-like ontologies for QFT would be something like the thing that I articulated this morning, where we have a quantum field theory describes superpositions of classical fields. And it seems like you need something like a wave functional interpretation to kind of fully make sense of that. Although there may be ways of doing that without the full-blown kind of wave functional interpretations that I was sketching. Another option would be to kind of go back to more traditional, either algebraic or kind of Whiteman formulations of field theory and say what we have is a field of determinable quantities across space-time. And then think of a configuration as some kind of state on that, maybe an assignment of expectation values or something like that. And then you can fight about whether you have really a field of expectation values or a field of operators whose values are determined by expectation values or something like that. And then the third option, which is the sort of thing that David Walsh and Chris Timpson started talking about, at least at one point in the past, was some kind of field, not of operators, but field of quantum states, maybe field of density operators or some other quantum state-like object across space. I think that could also be an interesting avenue, especially for someone who's interested in like wave functional realist interpretations of non-relativistic mechanics. So I think those three options should all be on the table and are worth exploring.
Oh, yes. Well, I would be inclined to say that the right way to establish an ontology for QFT would be to choose some solution to the measurement problem, and then that will at least indicate strongly what the associated ontology should be. And I guess I sort of set out my view this morning. I don't know if I think there's any existing approach which I am fully satisfied with yet, but there are interesting possibilities. So maybe at some point in the future I would have a more definite answer to that.
I'm very epistemic in the way I think, and I'm also very operationalist too, in the sense of the standard approaches to ontologies of QFT. I would be the closest that makes me satisfied in a way is the one with Whiteman reconstruction, talking about local algebras of observables, and indeed quantities that are measurable. We have quantities that are measurable in a QFT, and those quantities that are measurable are given by the endpoint functions and expectation values and those, right? So for me, that it feels to me that that's the closest to element of physical reality, because I not as much understand this as fields of expectation values living in different places, but rather as there's something that I heard once in a talk that I actually forgot who was giving it, which is unforgivable. But if we are good physicists, we should be able to recast all the physics in terms of the outcomes of measurements of the readouts of clocks, readouts of rulers, at least locally. And that is the kind of non-ontology, or whatever you want to call this, that I would give. So I'm definitely closer to the algebraic view. Like elements of local. elements of local algebras, Q operators mirror over smooth enough functions that are localized in space and time, and measurement outcomes associated with things that can be measured.
Okay, great. So that's a big space. Views. Maybe to get us started, can I ask a question, or actually bring us back to a question that kind of came up this morning, where I think, Noel, you were asking Eduardo about what it would mean to take the endpoint function or expectation values to be at least an ingredient in the ontology. Can we circle back to that? Because I'm not yet, to me, I'm not sure I fully understand. So, okay, yeah, if you guys could revisit that issue, I think it might be a good place to start.
Yeah, so I mean, I guess I thought, the worry is, I mean, I agree, I like playing around with the Whiteman formalism as a potential kind of framework for QFT. But I feel like every time I look at the Whiteman functions themselves, at least the way I understand them, is correlations between some other kind of local quantity, right? These local field operators. And so it seems like my grip on the field-like content comes from that perspective rather than just taking the Whiteman functions as, for one thing, it's like you can extract all the information you want from the Whiteman functions, but you have to assume they have all sorts of special properties. And a lot of those special properties seem extremely unmotivated unless you think of them as arising from the structure of correlations between something like a local, classical-ish looking, within reason field.
So for me, it's true though that for intuition purposes, I often talk in those terms, like all the time. But you see that I'm of the opinion that it's possible to, so we do have inherent limitations on our resolution of a quantum field. At least as much as we think of our measure of, we don't talk about time being emergent. If we have a space-time and then we do QFT on it, right? We do have a limited ability to resolve time and space. So those objects that we are discussing to be the ontology are not really measurable, are not physically accessible in the sense that the local observables are not really accessible in an experiment. Any experiment will be a smeared operator that we measure, right? So in that sense, I believe perhaps that we should integrate as physicists, right? Or I'm a physicist. The inability to resolve as part of our fundamental description of it. Maybe that's helpful also from the point of view of trying to understand better gravity and those things, right? The ability to measure and to resolve those things. And that's why that would be my, if I'm telling you, I do use as intuition, thinking of wave functionals and talking about the Wellman function as two-point correlators between regions and so on. But integrating those objects that we talk about ontology are not objects that are accessible from the physics point of view in an experiment. You will always have some resolution limit. So in a sense, I feel that it makes more sense to me to think about those limits of localized, if you want, observables. Maybe thinking of new avenues of like covariant cutoffs to measurements. What does it mean? What are the fundamental limits of the measurement that we can make? And that will tell us whether how much we can actually reconstruct a QFT based on experiments. So in that sense, I'm on the operational side, but I do think that to me that's why it makes more sense. Even though again, I tell you, I do use this for intuition. I don't want it to be understood as, oh, I think this is bad. It's actually really good. We use the intuition all the time in physics to come up with new things. In terms of ontology, I do struggle with those things.
Mike, we had a student who had a hand.
Okay, so yeah, let's Paul, and then I've got a few people the queue building. So Paul, just make it away.
Yeah. So my worry so I was thinking if we take fundamentally what that the ontology is mainly the correlation function. I'm worried that, so what we're doing, I'm going to do an analogy, is if I want to understand why Socrates is mortal, and I just say all men are mortal, I'm just restating more facts. And I'm not explaining in this, I'm not really having an explanation. And the correlation function just seems to be more like a systematization of facts in this operationalist way. And you're not grounding where the phenomena is coming from. If what I'm saying makes sense. So it just seems like by saying my correlation function is what's part of the ontology, is just in some way seems to be restating the phenomenon.
Yeah, so that sounds similar in spirit to what Noah was saying.
Except for I wouldn't think it's even that correct. Because I think actually the way that the correlation functions in code, what's experimentally accessible, is not very, I would say it's not actually very correct. Like we can construct things to be observed in the correlation function. The correlation functions themselves are already highly ideal on these objects.
In the sense that you have to pass the house through LC.
Yeah.
So maybe I'll comment on this, right? There are so I do believe, and again, when we talk about observables of a physical system, how they interact with the rest of the world is important for a description. And certainly in the interaction, if you go to the fundamental interaction between quantum fields or even like particle detectors, quantum optics, how atoms interact with the electromagnetic field, you do see when you solve the dynamics that you have the two functions on the board that we're seeing there. I think it's more direct, perhaps, than said, in my opinion. And also, relations between the interactions between the objects that we use to measure, which are physical systems themselves, and the things that we're measuring should be important to describe an ontology. So I disagree on that the statements are two different statements. See what I mean? Like, I don't know. I don't know if that helps or not.
Wait, let's have David.
I mean, this is just a thought as to what the question is supposed to be. I mean, there's a very coarse-grained sense of it, I understand. I mean, at that very coarse-grained, I could, when I'm asking you, I want particle or field description, I could be saying something like, well, is the algebra of operators that characterize the theory to be thought about as having its relation to space-time because it associates algebras of operators or operators to space-time points, to space-time regions, or is it more structured the way particles are structured? Does it give me a Fox-based type decomposition, and does the space-time connection come in terms of the action of the translation of the quantum group on sectors there? That's something I can get a grip on, and something that's a technical question I can look at. I can see once you move to an interactive framework where they stop being dual, and think what's going on in claims, you think this way or that way. But a lot of these discussions end up being finer grained than that, and it's like, okay, I've got my mathematical characterization of the theories, observer algebra, but I'm not done yet in my ontological game. I want a deeper understanding of what's going on. And beyond the pragmatic, I'm not fully sure I know how to understand that set of questions. And my reason isn't just a sort of brute operationalism, it's that these are not fundamental theories. We know that the right way to, we have a very strong way to think about quantum field theories is they're effective theories that are descriptive of phenomenology on certain length scales, that are largely neutral as to how the physics gets filled in on shorter length scales to that. So if I had two rival theories of the ontology of a given mathematically realized quantum field theory, and they're both effective field theories with respect to whatever deeper theory we're not considering at a given time. I mean, even if I have fairly thick metaphysics, even though I'm not going to just generally wave my hand and worry about understanding metaphysical questions, what's the right way to think about the factive questions, which of those is the correct ontology, except insofar as the answer is just sort of middle is, well, neither is. If by ontology we mean some sort of metaphysically fundamental cuts nature of the joints, whatever description, then of course no theory we have at the moment is a real candidate to deliver that. If we don't mean that, then what exactly do we mean if we want to get a finer grained description than just say, well, this is the mathematical structure that characterizes the theory? That's not necessarily a rhetorical question, but that's the puzzle.
Yeah, I mean, I guess my thought is something like, I'm totally on board with that project. I just think that one important way that we might play that game is first by interpreting what the theory looks like as a fundamental theory, and then trying to understand the ways in which the theory as emergent departs from what the theory as fundamental would be. And part of the tricky thing in the relativistic QED or QFT cases, it's extremely hard to understand what any of these things look like as fundamental theories. And maybe the eventual moral is they're incoherent as fundamental theories, but that would be an interesting discovery that I don't think we're going to make just by sticking with effective quantum theories. I mean, for one thing, like one of the worries about one of the worries that I have about some of the other, like even like straight up algebraic QFT approaches to the ontology question is, when you actually like look at a compact region of space-time and think of the theory as an exact theory, it's really hard to figure out what the local observables are. Like the things don't look like ordinary, I don't have local charge operators, I don't have local energy momentum operators. Like things I might think of as local vehicles suddenly are no longer in the local algebras, and that starts to look extremely bizarre. And that sort of disappears when you move to an effective field theory standpoint to some degree. But I would like to understand, what would an exact theory like this look like, and how would it compare to an effective theory where I have something like an effective local.
How do those disappear from an effective field theory? Sorry, they're not.
Oh no, I'm having to think that they might, because the sorts of, like as soon as you start like not worrying about like, separating the algebra in some double cone for like his exact space-like complement, but like shift the space-like complement out by some finite amount, then you can start to approximate things.
You're thinking, okay.
Next up, James.
Yeah, I'm just going to raise some very similar points to David, really, but I guess I'll expand and maybe try and give some kind of devil's advocate argument to why. Well, it's more a puzzle that I have. Anyway, yeah, okay. So, I sort of very much shared some of the worries that David was having. Well, I guess one way to put it is, from an epistemological point of view, it seems like the fundamental ontology of the theory, if we identify that with, if we identify fundamentality with very short length scales or arbitrarily short length scales, we have good reason to think that's not a well-supported part of the theory. That's not what we should be committing ourselves to. From a scientific realist point of view, that's not kind of the stuff that we would want to attribute to the world. So that might motivate you to think, okay, maybe we shouldn't be focusing on fundamental ontology and fundamental metaphysics of QFT. We should have some kind of effective metaphysics, something called effective ontology. And that's sort of what Porter says in his Making Scientific Realism Effective paper. But then one question is kind of, what is effective ontology? How do you characterize the non-fundamental content theories? Porter doesn't really have an answer. It's not as fun in hard times, not here. But, and in my papers where I kind of explored some of these ideas, I actually talked about the correlation functions, the endpoint functions, as maybe that's one way of saying what the kind of low energy content of the theory is, or the long length scale content is. Basically, like relatively long length scale correlation functions. But then an empiricist might come back and say, okay, but how is this metaphysics, how is this ontology? Isn't this just kind of encoding empirical content? So I guess maybe one of the as a kind of potential answer for why we should be interested in fundamental metaphysics would be that in order to characterize the non-fundamental stuff, we kind of have to have some account of what's fundamental. Because, well, at least a lot of the ways of characterizing non-fundamental stuff seem to be kind of parasitic on fundamental. And so it could be that there's kind of a semantic motivation for saying something, at least having some options about fundamental ontology, even if from an epistemological point of view that's not what you're going to be committing yourself to. So maybe you need a fundamental ontology kind of as an intermediate in order to tell you what the non-fundamental stuff is, and then that's kind of a lab you can throw away at the end of the day when it comes to what you actually commit yourself to. So yeah, I'm not sure if that makes sense, but I feel like part of the issue here is that epistemological motivations and semantic motivations might kind of lead you in slightly different directions into different projects. But I'm not sure whether Noel agrees with that or not, or has any thoughts about any disagreement or agreement with what I've just said.
I would probably say I partially agree. I think there are cases where that might be the case. Although more broadly, I would just think that there are situations where even the semantics aren't wedded to what the exact fundamental theory looks like. But to understand epistemologically what the effective theory looks like, it's helpful to understand what a fundamental theory looks like. And I mean, I can have semantics just that.
I think David has a finger on it.
Yeah, I mean, just briefly coming back to that and coming back to something everybody said, I do think it's important to say that there's not a dichotomy between, if you like, the sort of brute stuff that the empiricist is happy with on the one hand, and a sort of full, rich, as metaphysics as you like, ontology on the other hand. I mean, the information encoded in the correlation function data is telling you stuff, even understanding the expanded model as an effective field theory, is telling you stuff about the microstructure of the vacuum and excitations at femtometer scales. There's no version of instrumentalism I'm familiar with in which that stuff is just directly in the manifest image or the O language or whatever. It's, the Van Frasinian notion of what an observable is way, way more coarse-grained than this. I mean, the issue is something like, is there more to say than to say the full mathematical structure of the theory? The full mathematical structure of the theory enormously exceeds the directly empirical content of the theory.
Let me put it this way. I'm a physicist, so maybe I have a certain difficulty understanding some of the points here. I feel much more close to what Emily said, or what you said. Let me put it this way. If I take a quantum theory, not a field theory, quantum theory, and I ask the question, what is the ontology? Okay. First of all, as has been said, it seems that it makes sense to us what is the ontology of quantum field theory unless we first declare how to answer the question about relativistic mechanics. In classical mechanics, if I have the theory of one particle of a solar system, there's a mathematical theory and I have a clear ontology in mind. And I get the impression, something wrong, that while the philosophers are arguing about the ontology of some quantum stuff, and sort of nostalgia for the classical picture, which is emerging. Because, we get to the point, if I have an relativistic, let's take a one particle, is that a superposition or position of the particles? Is that ontology? No. I mean, the ontology of this theory is that it's a quantum thing to which I don't have to force it into my intuition, I have to adapt my intuition to it. But there is something very clean I know about it, which is there's a certain quantity which I can observe, which are the position, the momentum, the energy, maybe the angular momentum. I know what it means to observe that, because I know the kind of interaction I have to do. And what I'm talking about is the system that we characterize by these quantities, which are characterized by the fact that they correspond to non-Newton operators, so they cannot be shot together. So at the same time, I can think of this object as a superposition of position or superposition of energy in values. Okay? And if I try to say something more than this, I think I'm saying nonsense. There's nothing more about particle than this entity, which can at the same time be sharp in energy as well as position or vice versa. It's not that behind that I have to guess something else than that. That's it, as far as we know about the world. Maybe we'll discover that the moment are right, and then there's another story to be told. But as far as quantum mechanics, now if I had this attitude with respect to non-relativistic quantum mechanics, when I go to quantum field theory, what there is to discuss? It's exactly the same. There are many possible bases I can choose. There is a basis which I can measure. Okay, and another basis I can measure and corresponding operators that I can analyze, and each one of these tells me how this thing, which is a quantum field, behaves. So quantum field is a thing, is itself, which is characterized by non-polluting observables. Some of these observables are the particle number, which by the way is just an integral of the field and its derivative in some operators in it. So I know exactly what it is to measure it. I know how to measure the energy in that CERN and how much, and therefore in which sense, how much local particles are there, which are not quite many particles, of course, because this is a local measurement. And I can measure the fields. The field in a small region. And if I measure the field, that's exactly what is being measured by particle detectors. If I measure the field, and then I come to the correlations. It's not that maybe there was a misunderstanding here. When I hear the ontology is the correlator, it doesn't mean that the ontology is correlated. It means that the correlator tells me how to think about the ontology. The correlator is something which implies two measurements, not one measurement, say, in one function. So if I measure this and at a certain number of time and this at a certain number of time, I, in theory, give me predictions about the number of times they agree, they disagree, and so on and so forth. So this is telling me that one possible thing that I can observe is the local algebra of observables, and this is a basis, if I choose suitably. So what there is more to add to it than exactly the theory is telling me about the quantum object I described is the object which is described by these local observables and can be observed on different bases. Why want to add something? And finally, about the quantum theory as a effective theory, of course we don't take current quantum theory as indication of what happens also with Tabaret and etc. I'm fully buying all this. Nevertheless, we can take electromagnetism in a box. That's the quantum field theory. I know it's observables, I can compute everything, I know that there are particles, basis, I know that there is a field basis. It's nothing to do with the ultraviolet. I know that if I measure a smaller and smaller region, there is something very interesting that happens. That's absolutely true, because in vacuum state, which is an outcome of measurement, you measure the electric field here, I don't get zero, then the smaller it is, and so on and so forth. But there should be a clear interpretation of quantum field theory also independently of the fact that, in this case, independently of the fact that the interacting field is only the total value as effective fields. So that's how I would think about the problem. Or maybe I'm missing something that wasn't
I think I agree with most of that, but I think the two halves of that are more closely related than perhaps you think. I think if you have the take on what the ontological content of the theory is, that more or less says, once you specify the observer algebra structure, there wasn't much more to say, then I think the problems that arise from thinking effective field theory aren't much of a problem, because the task of recovering the effective field theory from what's underneath precisely is the task of recovering the observer structure. So you've got a way of thinking about ontology that's robust against theory change. And I think that's sensible, that's what you should look for. The concern I was raising was if one's notion of ontology is finer grained than that, if for instance it involves preferring one basis over another, then it becomes much less clear that will survive theory change, even if it's about other reasons why one might be concerned about that as a strategy.
Patrick.
Yeah, so I was interested in this proposal that the ontology of quantum theory as being sort of composed of the correlation functions. And I've got a bit of a worry attached to that, which comes out of something that happened in quantum information theory, where some people sort of propose interpreting quantum information theory as, well, like the fundamental ontology is just information, and that's it. And a lot of those proposals were sort of made in the spirit of sort of radical departures from tradition for doing metaphysics, but I think they're more just confusions, because the natural question to ask, if what's in the world is just information, then you can say, well, information about what? And so then you have to fill something in. And I worry that if we say that correlation functions are the basic elements of reality, then you're sort of subject to the same kind of question of like, well, correlations of what? What is the thing to which this is attaching itself to? And so even if we follow Carlos' suggestion that we don't need anything more than the minimal kind of thing that's sufficient to reproduce the observable things in the world, we still need to distinguish between the features
terms of our observations and the things that those observations are supposed to be attaching themselves to. And so I guess I'm confused if the ontology of QFT is just like what exists are correlation functions. I don't know how that can make sense without saying that there's something underneath them.
So you see, I mean, this is like what we done. I would see also the reciprocal danger, right? So if you restrict, if you are saying, imagine that I were saying, okay, let's restrict ourselves to the elements of the local algebra that is enough to describe the experiments that I'm doing and measure the quantity that I'm doing. You say, well, you may be missing on what they attach to. Perhaps if you try to fine-grain that, you can be adding things to the theory that are not fundamental. In projecting prejudices that may come from other ways to understand, like classically the world. Like for example, perhaps I'm not saying it's like this, but perhaps it is impossible to have an ontology of QFT without telling me how I measure the QFT. You see, that's a great way to say it. Without a measurement theory. Like, what are the kind of apparatuses that are fundamental that I can think of the LHC as being, the sensor in the LHC as part of them, the same way as the retina in my eye. All the apparatuses that we use, what do they have in common? And how they couple to those fields and the interaction. So perhaps thinking of a free theory and fine-graining a free theory, a free theory. Perhaps the danger, if you take the, let me call it conservative. I subscribe to what Carlos said. I don't know if it's criticism, but if we get the conservative physicist approach, it's like, well, enough to explain every experiment that I can think of, and that's it. Why add more, right? If you don't, you run the risk of either missing parts, or oversimplifying the fine-graining,
or directly missing part of that is important to the ontology. For example, how do we actually figure out those numbers? Through interactions, of course. And what does it mean to interact? And should it be part of the ontology as well, right? I mean, in my opinion, though, I think that is talking about the local observables and the interactions that allow us to make measurements, and how those interactions update the field, like real. What does it mean when I obtain information about the field? And I mean, information about the field means I want to measure the field amplitude, and I couple something to it. And through processing that something that coupled, say the retina of my eye, right? I end up with a number 7. At some point, some magic happened, whatever, and I end up with a number 7. And now that I know that it's number 7, how do I describe the field? All that, I would say, can be done more risk-free if you focus on the local observables. And then you find, what is the interaction with detectors, what are the POVMs of the field that are induced by those interactions, all in terms of correlators or expectation values of local algebra elements. In my opinion, there's the danger that you describe has a reciprocal danger, right? Of missing out on stuff if you want to fine-grain too much.
I mean, surely just the possibility of error is not in and of itself a reason to not ask the question. For almost any question you might ask, there's a possibility you will get the answer wrong. That doesn't mean it's a bad question to ask.
No, that's not what I'm suggesting. What I mean is that fine-grain in particular, like I'm thinking more of description in terms of something like a wave functional, without incorporating. So if you want to fine-grain beyond the smear operators of the field, local smear operators of the field, then I think it's not enough to talk about the field theory in itself, but you also need to talk about the apparatuses that you couple to those fields.
Yeah.
That's what I mean. Not that the question should not be asked, more that if we try to fine-grain too much just on the ontology of the QFT in itself, we may be missing some part, which is the extraction of information from the field, which should certainly play a role in this.
I mean, I think part of the issue is that at least if you're a strict reductionist, then ultimately you want to say that the observers and the measuring devices are made out of the same thing as the quantum field. It's not another layer of stuff, right? It's all the same stuff. And so if your ontology is just correlation functions, it becomes so mysterious how observers and measuring instruments could also be made out of correlation functions. It's sort of an infinite regress in which everything is a measurement and nothing is ever measured.
So it's like a Heisenberg cut kind of thing. You see, like at some point it connects with the measurement problem of quantum mechanics. Like how,
So, yeah, certainly it's going to.
Yeah.
Yeah.
So I agree with that, right? But then again, it hits the same problem if you want as classic quantum mechanics, I guess.
Sure. Yeah.
The extraction of information seems to be important, right? Like when we describe a quantum system, not only the evolution dynamics of the quantum system and the coupling with apparatuses, but also at some point we are assuming that we have some information. Some experimentalist writes on a notepad that is a number 7 or 42 or whatever it is, and we have to incorporate that to the description, right? The state update thing.
Yeah, I definitely think there's not much point trying to talk about the ontology without incorporating the description.
Next, I have Adam.
Yeah, so one thing that we talked a lot about like fundamental ontology versus epistemic access and these sorts of things. But I think, so even from a sort of more effective field theory view, there's still a notion I think that's maybe more intermediate of like relative fundamentality. And so you can say, so if you hold the view that our current best theories are effective field views, are effective presumably to some other theory, and there's a story to be told about what the natural variables, observables, ontology, whatever, of that theory is and how that relates or emerges or gives rise to, I guess, if it emerges from, gives rise to the sort of observables, the field content and stuff we have now. And so I think one thing that hasn't been talked about that I just kind of want to throw out there about thinking about what the ontology of QFT is that we can think about relative fundamentality and how at one given level, we don't have to think this is the once and for all story. We can think very amenable to the effective field theory. At a given energy scale, what are the natural fundamental can just mean the most natural variables, the things that Carla talks about, that like what's the minimal description that gives rise to what we can observe, and then how does that relate to other levels? And I think that's an important role for ontology of any given theory, not just in an effective field theory framework, but you can say, how do we get classical out of quantum? How do we get non-relativistic quantum out of quantum fields? How do we maybe, and then you can kind of turn that the other way to think, how do we get, just kind of getting back to Rhoda's talk a little bit, how do we constrain the quantum or quantum gravity or something like that from what we think of as the natural ontology of quantum fields?
Yeah, that I think brings us back to this question, non-fundamental ontology, and I guess part of what you might wonder about the question that's central in this discussion is if we are construing quantum field theory as effective field theory, or particular models we're interested in turn out to have to be effective field theory, what influence does that have on the nature of the prompt? Like, what does the realization that quantum field theory, while we might have aspired to use it as a fundamental microphysics for all of reality, turns out not to be that sort of thing, does that change the project of in articulating an ontology for the theory? That seems to be circular in the background. Okay. Any of you want to comment on that piece? But
I would say, the lines as was said before as well. I think it is important to understand, to try to understand ontologically the theory, to see what fails, if something, if we want to go beyond it, right? And maybe one of the problems with quantum gravity, we've been trying to do quantum gravity for a long time now. We're not extremely successful doing it so far. Maybe one of the problems is that we need to think a little bit back about relativistic quantum mechanics and understand better what's going on there, what fails. Maybe that will give us a better understanding. I think it's important though, asking those questions.
Yeah, and I think we have and find useful ontologies in many other bits of science, which we would presumably also agree are just effective and emergent. The ontology of the atomic theory of matter and its atoms, and that seems like obviously correct, even if the atoms are not fundamental, and that is a useful way to interact with the theory. So I don't see why QFT would be any different in that regard. We could have a correct and useful and effective ontology, even if it's not fundamental.
David, do you want to comment on that?
Yeah, I mean, I think the question sort of brings up what I think is a bit puzzling about the fact that we might look for to try to get an ontology out of these theories as if they're fundamental theories. So, fine. Let's say that what we're doing is just lattice QFT. Let's pretend lattice QFT is a fundamental theory and try to get an ontology out of it. Of course, it's totally unrealistic to suppose it's a lattice. Nobody thinks there's really a lattice. But so what? We were supposing our exercise was we start by pretending that it's a fundamental theory and then go from there. And QFT on lattice is enormously better behaved and easier to handle or mathematically tractable than the various continuum theories that the Noel was discussing, for instance. It's a nice, fairly mathematically well-defined theory. So if the job is in terms of theories, it was fundamental and mutually effective, let's just put the theory on lattice and get home. But that doesn't seem to be what people have in mind. There's some sense in which the project of interpreting the theory as if it's fundamental doesn't allow that kind of move. And so this is just like a peek at what exactly is this project.
This is super interesting. This may it also has to do a lot with the attempt to put a fundamental of gravity in place. I don't think we're fake. I think we have various options, a number of options. We don't know which are in the dark. There's no damage. But I think that when we try to, there are two projects that we're trying to construct quantitative theory of gravity. This is the core of what we're saying. One is, okay, let's see what's down there, the small concept. Lots of physicists think that that's the wrong project. The right project is the gravitational field at some scale, large, that undergoes some non-perturbative perturbative, just the same. It's just that there are no interesting phenomena. The gravitational field at some scale, and the theory tells me what is the quantum behavior of this thing. Okay? Maybe with hints from let's normalize some constant. But it seems to me that an interesting project in physics, it's always the second one, and not the first. The interesting project in physics is to describe the physical reality as scale never accessible and construct a credible story. That seems to me the promising and the project that de facto has worked in the future, even rather than trying to understand the ultimate reality down there, including in quantum gravity. So it's not that oh yes, but when we figure out quantum gravity, we have the ultimate reality. When we figure out quantum gravity, we have a tool for describing what happened at the end of the vibration of black hole or in the universe, which are phenomena that happen at time scale. And hopefully we'll have a good theory, which means also a good sort of partial ontology, I don't know what the language that we're using, a way of thinking about what happened there, a handle on there, a certain number of variables, an intuition about how this variable behaves, and this gives us the idea of what is there. That gives us the best picture we can access as adjusting our intuition to the quantum.
Wayne has a big reference as well.
Yeah, I think a lot of what I'm about to say has been foreshadowed what other people say, but I think it's worth reinforcing. So the word fundamental gets thrown around a lot, especially in the metaphysics, the physics literature. People talk about it as if they know what fundamental physics is. And I think it's worth emphasizing that not only do we not now have a candidate for a comprehensive fundamental theory, this is not a new situation. There has never in the history of science been a candidate for a fundamental comprehensive physical theory. People sometimes talk as if the quantum revolution was some expulsion from an Arcadian paradise where we all agree on what the ontology, basic ontology of the world is, and people who think that often talk about the ontology of classical mechanics, and they think it's point particles moving around. But continuum mechanics has always been part of classical mechanics, rigid body mechanics, and if you go to the 19th century, no one thinks that they have an account of what things are like at the fundamental level. Even people who believed in atoms, and that was controversial, some of them were continuum theorists that atoms were vortices in this incompressible ideal fluid. And we'll probably never have a theory like that, a fundamental theory. And so that raises the question of what the methodology and purpose of metaphysics of science is. One thing you might do is take your best theory and treat it as if it's fundamental, in which case what you're doing is a species of fiction. I think if you're writing fiction, then you should be judged by the standards of fiction, and on plot and characterization, and I think it falls flat. But David says something that is really worth emphasizing. I think we can draw conclusions what the world is like, but they should be cautious enough that we think that they're robust under theory change. Like, so if you read Newton's Principia, what does he think there is in the world? Well, among the things he thinks in the world are Jupiter and Saturn, etc., moving around and having certain trajectories, and that's true. They do exist, and they at least are approximately on the trajectories of Newtonian mechanics say they are. And okay, that I think is actually a conclusion that is going to be totally safe from theory change. Right? Another point is, well, then, okay, if we ask questions like ontology of quantum field theory, ontology of quantum mechanics, okay, I think it's not a good question because quantum mechanics, as we have in the textbooks and quantum field theory is essentially the non-controversial core of it is basically operational. We learn how to associate states with preparation procedures and do revolutions and do experiments, calculate the possibilities of results of experiments, and all the various apparatus we have, insofar as it uncontroversially has physical meaning, gets its truth connection with observations. And I think one could ask for more. Like, what is the world like? But I don't think that quantum mechanics, as we have it in the textbooks, or quantum field theory, as we have it in the textbooks, is aimed at giving us answers to those questions. Those are going beyond what we have. You might not want to go beyond that, right? But if you do, then I think I think Emily said this. There's no interpretation neutral way of doing it. If you're actually adding something to the quantum formalism as we know it. So, I don't think we should be asking what is the ontology of quantum mechanics, what is the ontology of quantum field theory, because it's the formalism as the physical theory as we have it sort of stops where certain ontological questions start.
Kind of keep track of all the things you respond to. Just to go back, to one thing that Dave said earlier, I have no problem treating quantum thermodynamics as a fundamental theory and seeing what that would tell us about the world. In fact, I think it's probably a very useful project. One question is just like, if you think you've got certain kinds of effective theories, which ones should you pretend are fundamental that might give you some interesting glimmer into what the effective theory is helpful? That's one kind of interesting fundamental question. But I think in the QFT case, there's sort of another sort of philosophical foundational question that's sort of taken over a lot of the kind of rigorous foundation literature, which is, we thought it wasn't going to be this hard to come up with sort of exact unifications of special relativity and quantum mechanics. And it turns out to be even harder than we sort of initially imagined. And now there's this theoretical question, which is like, what are the limits of sort of exact reconciliation? And if that seems like a perfectly legitimate interpretive philosophical question, whether or not it's going to tell us something about what our effective field theories are saying about the actual world. I suspect they probably will, but we can fight about that separately, right? I think it's a worthwhile philosophical question in itself. And this is sort of similar to if people worry about the metaphysics of contact interactions and exact rigid body mechanics or exact continuum mechanics. This is probably not going to tell us about the metaphysics of interactions in our world, but it's an interesting philosophical question as a philosophical question. That's one of the luxuries of being a philosopher. You do get to worry about counterfactual or fictional, if you will, worlds. And part of the reason might not be so, mundane. It's just these are interesting worlds to think about. But if you're interested in questions, sort of broader questions about scientific explanation or the structure of theories or the nature of deduction or the nature of laws, plausibly the answers to some of those philosophical questions will hinge on counterfactual physics and not just actual physics. And so I think it's worthwhile to explore things for that sort of purpose. One thing I was going to say about Carlos' point from earlier, which is that, what more could the philosophers ask for than stories about the local algebra? I think one sort of worry is there's too much stuff there. It certainly can't all be fundamental. If it were all fundamental, that would be a very, very surprising, weird-looking theory. And so, I mean, one way to get at this is like, if you think the story is going to hinge on a resolution of the measurement problem, many resolutions do require privileging the basis or choosing some set of more sort of privileged quantities out of your thing.
Not the best one.
Well, yes, ones do not require it, but there's this debate now about whether, yeah. I mean, that kind of has virtues of different interpretations of measurement problem. The point is that insofar as many of the interesting ones do seem to privilege this, that's one thing that they might want, is a story about. But I would even argue that
Maybe that's why it wasn't aesthetic. Maybe that's why it wasn't aesthetic.
Well, I was just saying, even if you're, I mean, I suspect if you look at the local C-star algebra of quantities in any reasonable quantum field theory, it's just a grab bag of all sorts of different stuff. And there's no way all of that you want to treat as equally fundamental. Right? Maybe you want to shift back and forth between like position, momentum, representation, but the analogy of the classical field here would be something like you've got algebras of quantities on symplectic spaces, and you're going to treat the local algebra of like functions as equally fundamental descriptions of the EM field, and that strikes me as madness, at least in the classical fields. It may be the case that's worthwhile for QFT. Sorry, there was an interjection there.
Yeah, I understand. Why would that be madness?
There's just too much stuff. Yeah, it's especially like gross.
Space, that's why it's dilemma.
No, at each region. No, I'm totally fine with there being all of this stuff across the region. It's just that, like, I mean, when we think of like ontologies for classical fields, we typically think of like an assignment of vectors or scalars or tensors to points to regions, and then all the other stuff you want to talk about are functions of those things. But we don't think of the functions as themselves being equally fundamental as the EM field. That's the kind of story that I think a lot of philosophers are looking for out of something like quantum field theory is. What are the kind of more fundamental parameters out of the sort of, at least what many of us take to be obviously oversized bags of attached points and regions?
This is mirrored field, the same as space fields. It's just mirrored field.
No. So there's a huge shift between talking about, say, like the local Weil algebra, maybe the local Weil algebra is good, like the Weil unitaries or the local field operators. That's already to choose very specific quantities as the fundamental ones. The kind of view I'm saying is like, suppose you take like the net of C-star algebras and take the complete local C-star algebra or the complete local von Neumann algebra. That's a huge object. It's going to take all sorts of things that we would not think of, at least classically, as fundamental physical observables.
Okay, so I've got lots of fingers. I want to make sure that we at least get through the original queue. And I'm sure that the fingers will find something to attach to. Doreen.
Yeah, so I'm going to shift a little bit. Sorry for the fingers, but so I kind of want to answer the reasonable questions posed by the physicists and by maybe banning for the moment the word ontology and fundamental versus emergent, and then I think this does get into very like metaphysics-laden discussions of what those things mean. But so Eduardo, you had a nice answer to the question about like operationalism and the about information and about the importance of the operational side of thinking about the detectors and how they couple fields and how that's a way into understanding for you what you're working on. So I wanted to push you a bit more though, because I don't think of you as an operationalist, because you just gave this really nice talk with subtle points about how you apply different models in quantum field theory, right? So instead of talking about ontology, let's just talk about how we're going to model things that you care about modeling. We don't care about fundamental scales, right? At the scales, you want to model things. So do you want to say a little, I want to invite you to say a little bit more, like we understand that the operational part, there has to be a tie to the operations that you're going to do through these detectors. But what kinds of things do you think about when you're setting up your model of what's happening in the quantum field that then you're going to want to couple the detectors and then try to figure out some way to operationalize that way?
Okay, so try to be brief as possible with that, because I feel like I suspect I'm going to have a lot of
I have one here. I have some detectors. I think that
you asked me how I think
is
about it.
when I'm doing
I do think, and that's the
And those detectors
that
couple
I have there.
local elements.
That certainly in the description
And the coupling in itself
of,
already modifies the list.
or in
It
general
says, you know, there's the
observables,
coherence.
one is to include the interaction with detectors,
That coupling is selecting out.
whatever we're using to measure it, to the point that even fundamental. So the way I see it is,
We're not allowed to use the word fundamental.
fair enough, forget. So the way I see it is the following. I have a quantum field, and I have some detectors, something that is modeling what I'm doing with the field when
Have
I'm
a
measuring it.
subset of observables.
And those detectors couple to local elements, elements of the local algebra observable. And the coupling in itself already modifies it. It
Dynamics of the system.
introduces, there's the coherence in the individual system the moment you couple. So that coupling is selecting a privileged edges, if you want, in a way, a privileged set of observables. It's not all of them, you see, the ones that are physical detectors,
Yes, I think.
which are actually really few.
Experimenter.
And we can argue
It's a
which ones
paper.
are okay and which ones are not. That's what kind of do.
What does that mean?
There's an extra
What it
process.
means is
there.
that, well,
That
the
process alone
interaction
already tells
itself
you one thing. Tells you,
evolves.
sure,
Some superposition.
you have a subset of observables you can measure in the sense of coupling detectors too.
associated with
In the
the
description of the
observables
coupling, the model of measuring that you have. You have an extra thing though. You have the full dynamics of the system, but there's something extra. The something extra is
eigenstates.
that it's not just that you couple
There's
detectors,
no collapse
there's something
here,
special. And again,
Just the dynamics.
having this at different levels would change the description, but there's something extra with the detector. The
Somebody
extra thing is that you have an experimenter
writes the data.
that writes a paper about the results.
So the
What does that
information
mean?
you obtain about the
What it
system
means is that, well, the interaction in itself will evolve the system to some superposition, entangled superposition of whatever eigenstate, whatever observables you want, associated with the observables that you couple to observables in the detector and observables in the field. The dynamics of the two things is going to evolve to some superposition, not to eigenstates.
localized
not to-
space.
There's no collapse here, no
And
projection.
couples, and I can
Just the
describe
dynamics of the superposition.
like couples.
But at
And
some
now I
point,
can measure those detectors.
somebody's doing the
Now,
experiment and
detectors are
that will be-
selected so that
and
you
write
can
the
measure
data,
them using
right?
derivatives
So the
of
information that you obtain about the system has to be factored in the
and
model.
use a projective method.
You have the coupling to the observables that you have selected because nature allows you to have. I call a particle detector or something, or detector. You want something, a quantum mechanical system that I have enough control to describe in a way that works and is
Measurements
compatible with the experiment,
made at
and it's
different
localized in space and time.
have to be
That couples, and I can describe the dynamics of the coupling with the field. That couples.
Update the field.
And now I can measure those
The,
detectors.
associated-
Now, the detectors are selected so that you can measure them using derivatives of Born's law, whatever you prefer. You can use it with, you can use a projective method. You can use
You need to
descriptive.
consider dynamics.
And that gives you some information about the detector, not about the field.
And
I'm
you
not
also
touching
need to
the
consider what information you extract.
But you have to take into account that
What does that
information
mean? That means that you
in order to describe the future state of the field. That's the
I
start
think
of
that I
it.
relax
You
the
need
quantum
measurements made at different slices in time have to be compatible with the previous what you did
Quantum
measure.
theory is effective.
You
I'm
identify the
agnostic
field
on what's
with the POV
But what I always have is
associated
experimentalist writing
to
number
having
7.
measure projective with
That's
a
what they're
detector, for
explaining.
example.
And
So
another
in my model,
experiment
without
is
using any
saying,
fundamental description, in my model,
and the correlation
it would be
function.
that. It would be, yeah, you need to consider dynamics with the detector that selects elements of the local algebra. But you also need to consider what information you extracted from the detectors. Now, what does that mean? That means that even if now, imagine that I relax the
Blurry
quantum theory, relax the
It's going to be
existence
blurred
of
by
the
the
quantum
rest.
theory. I say, quantum theory
You
is,
can even
I
describe
know
the
you don't want
causal
to use
structure
that.
of the space-time.
quantum theory is effective. Let me put it like that. I am agnostic of what's behind. But what I always have is experimentalist writing number 7 as a result of their experiments. And another experimentalist for the same, doing it at different times. And the correlation function using the outputs of those experiments that they can build. So maybe you can rewrite the whole theory in terms of those correlations that experimentalists had. And in fact you do, that's some of the theories that we have. You can write the full quantum field theory, blurry quantum field theory. It's going to be blurred by the resolution of your experiment. And you can even describe the causal structure of the space-time behind it, as Kemp and others have related it to.
So,
In a blur way, based on what you could measure from your detector. So I don't know if that answers the question you were asking. Or?
so you're going to have a model of the system, right? That, so so
What I assume is there.
there's three pieces that you just,
If you want to, if you say instead of a quantum field, what I assume
three
is that
pieces,
just
being the
a
model
set
of the
of
system,
local
including you said specify the dynamics of the field system.
that you can associate with a
And
quantum.
then you're going to couple that to the detector that comes important.
Models that
Then you're
couple
going to have an
detectors.
experimenter that
A
comes
set
in
of systems that are very controllable and I understand very well, and it's coupled to that select set of.
So, like, it's some
And
kind
the
of,
ability to extract
like,
information.
how you, there's an important question about just modeling, right?
Yeah.
Like, what you think is there in the world and how you set up your model,
Yes, I think
and
like
make the rest of it work.
So what I assume is there, typically inside.
I guess Yes.
If you want to, if you say instead of a quantum field, what I assume is
But it's
that
hard.
a set of local observables
I found it blurry.
that you
What
cannot see with a quantum
observables are
theory,
part of the
what?
ontology would be
Models that couple detectors to those observables, so a set of systems that are very controllable and I understand very well that can couple to that select set of observables, and the ability to extract information from those detectors. Those are the three things.
all of them are possible. I have strong
That
constraints.
is,
Yeah, so I think like ontology could be one, the first part, right, and then the rest.
I have a question.
I
You get to it.
I guess so.
How you accidentally access it, but
But
the
I
first
have,
part of it is in there, right? You need to have something called.
I found it blurry. I found it blurry because what observables are part of that ontology will be determined for what observables can you actually
You
measure,
ask
couple
me, you are
detectors.
a mechanic, right?
So for me, I have trouble separating
Like
the
some people
detectors
will tell you,
interacting with the
carburetor,
field you want.
No, but
from
how it
the
actually,
ontology of the field.
then some engineer would
Because that's what's going to select
the
some
gas
of
is
the
released by
observables.
the combustion goes.
Not all of them are measurable.
They will give an
I
explanation.
have strong constraints of observables that I would
I
declare
understand it.
measurable.
Somebody else may not.
I have a question
Why
though,
would the gas
quick
expand
one.
here?
Maybe.
Then
When,
somebody else.
when in philosophy is talking again, as
I know, it's
when we talk about ontology or metaphysics, or
Is the question answer when you're satisfied?
what is the final
Everybody
objective? To
agrees
be
with that.
satisfied with the answer? For example,
What is
if
the
you ask,
objective then when you look for an ontology? When does it end?
Nobody's gonna agree.
I see.
That's how you put it.
I would think that in a lot of the philosophical question debates, the goal in many cases is not to figure out what is the right picture, but actually just to understand what are the possible pictures. Because oftentimes we see sort of like a handful of possible pictures, and it requires a lot of work to see beyond the dogma the other possible pictures. And then it's hard to actually figure, if you think the ultimate goal is to try to understand what might be the right picture, or we have good reasons to believe that one of these pictures is closer than another. It's hard to play that game when you don't understand the space of all possible pictures.
I see.
Yeah, so similarly, I think that often when you do physics, people have an ontology in the back of their mind, even if they don't articulate it like this, even if they would deny it if you ask them about it. And I think that doesn't influence your kind of the scope of possibility to consider when you do physics. So if you're considering trying to understand better what the space of possibilities really is, might help you kind of discard some bad assumptions that you're making without realizing it.
It's more in the journey in itself than the analysis than finding a particular thing that says correct, I guess.
I mean, the aim of inquiry is still to try to find something, or at least understand what we have good reasons to believe. But again, it's hard to do that without understanding what the options are.
Sorry, I don't know your name, but Connor. Thanks. I think there's three issues with taking an effective approach, or even treating it as fundamental even if it's not. So, what criteria for an ontology? I'm not going to propose an answer, but I will say that we would at least want unitarity, locality, causality, and Schwartz-Adds analyticity. And so the first thing with like unitarity, with like the minimal conditions that Carlo raised, we already have a problem with the number operator because like what do you do when you have physically or unitarily inequivalent representations of the particle content? Like how can that be? How can a number operator meet that minimal condition if you have physically inequivalent representations? And the second part deals more with locality. So, like if you, in terms of methodology for understanding QFT, you can take a Wilsonian approach or a Weinberg's approach. And Wilsonian would be like the more effective field theory, which seems to have been like what we want to kind of end up with as, say, or we might accept as, we'll treat as fundamental, even if it's not. At least Weinberg's approach, maps out the logic of QFT as what's unifying locality and or Lorentz invariance and quantum non-relativistic quantum mechanics. But if you take an effective field theory approach or a naive Lagrangian conventional approach, how do you satisfy? Like it doesn't seem like it works, or like you would at least have to demonstrate how you satisfy unitarity, locality, and causality.
Now, like how can something that is running into those problems, especially with locality and effective field theories, be treated as, like, what does it mean to treat that as fundamental? Even if it's not, I don't even understand what that would look like. Now, there is one approach that at least tries to address that. I'm not going to argue for it, but if you look at like algebraic QFT, not only has resources for satisfying causality or articulating it, but it also has recent promise with the other issues of like unitary and locality. So I guess my question with that is, like, what do you do? How can you treat this as, say, fundamental, or use a different word, we don't use fundamental, when it still has all these, I guess, serious issues, or what we might expect to support an intelligible physical theory?
Something I could say. So, for example, the first choice, I would say, yeah, no, the number operator is not one of the rules that I would consider part of the ontology as a valid rule. Instead, you would, so what you look for is, if you want elements of the local algebra, typically they're very smeared elements of the local algebra, in the sense that they don't have problems with, if you want, expectation values and correlation functions diverging depending on particular choices that you have. See, the number operator is for, and in fact, locality is an issue for a number operator. Right? I would say local elements of the local algebra, that wouldn't be an element of the local algebra, which is localizing the regional. So essentially, I think that algebraic QFT has already, QFT has already incorporated causality and instant causality. I think, again, you can have subsets within the theory that are well defined, become privileged in a way. And it's a physics privilege in a sense that those are the things that I can measure, right? That model well things that I can calculate. That would be my I don't see that many problems with that. So I would not choose a number operator. Not a number operator in the sense of not something that lives in the whole space thing forever.
Right. I think I almost yeah. I mean, that's just one part. Of the other part is that you still run into, or at least some effective filters still can't satisfy the color. And if that's the case, what does it even mean to treat that as a fundamental thing, even if you don't accept it as fundamental? For all practical purposes, like what does it mean to treat an effective field theory that doesn't have locality as fundamental?
I would not consider it fundamental. Well, fundamental is probably not. I don't like theories with locality. If you ask me whether I would leave earlier with gauging variance in my observables for locality, I would say both are very bad, but locality is better. It's better in my opinion.
I'll let David go first. Just briefly, I mean, an effective field theory defined on a vector scale L, it's locals within epsilon for L prime much larger than L. I mean, I agree if what you want is the deepest description of physical reality ever. That's probably it's not that, but if you don't want that, effective field theory is fine. It's not a deficit of the theory that it's non-local on scales on which you shouldn't trust it anyway.
Okay.
I can say one quick thing. So, like, one sort of worry, right, about this move is that the sorts of assumptions that are typically made in algebraic QFT or Python QFT are supposed to be specifications of assumptions that are be all over the place in textbook, ostensibly effective quantum theory. And if we were working with theories that were more well behaved, it might be easier to figure out how to relax those assumptions or fall back from those assumptions when we need to. The tricky thing is that actually fitting them all together turns out to be so hard that the worry is even when we do effective field theory and we say, oh well, as long as we move outside of, we let things spatially separate a little bit or outside of, the copper wavelength is
that scale, or we go to really long times. There's a worry that we may not have successfully avoided all the paradoxes that sort of sneak into the what we would think of as the sort of fundamental versions of it. And so I think that's one kind of special worry for effective quantum field theory is the foundations of the sort of the exact theory is so tricky that it's, I think, Dave probably disagrees, but I think it's difficult sort of to convince ourselves that some of these foundational words haven't percolated up